session, the mentoring session for the ITUA and Machine Learning 5G. So I would like to welcome you all for joining today's session. And as you all already know, these mentoring mentoring sessions are meant to bring some explanation or to just make sure that we bring to you the ideas, the techniques, the skills that can be helpful, that can be used for the challenge. So in some cases, we simplify the ideas to just make sure that the concepts can be consumed by non-technical people or for students, participants who are getting started in the challenge. So please bear with us because the techniques that we are going to present or we present to you are basic techniques, are basic knowledges. And I would like to welcome my colleague, Miya, who will take you through the session today on model building and training. So Miya, and welcome and good afternoon.
Thank you for the lovely introduction. I'm just going to share my screen. So hello everyone and welcome to our third mentoring session. This session follows the two previous sessions that we had in September. The first one was on a computer networks introduction course. The second one was on data preprocessing. The recordings of these sessions will be gradually coming out on the neural network and on YouTube. The first one should be out on Wednesday next week. However, as of now, you can find all the resources from the previous mentoring sessions in the GitHub repo, which will be posted in the chat. So last time, so 2 weeks ago, we focused on the data preprocessing section of the machine learning process. And this week we'll be focusing on the model training part. So as I've already mentioned, this left graph is from ITU Y.3172. This is a recommendation that explains how the ML pipeline can be implemented in networks. It's definitely a recommendation that I recommend you go look at if you have not seen it yet before. So today, our table of contents, what we're going to be talking about, we're going to be talking about machine learning types, machine learning model design and training, a hands-on Jupyter Notebook session, and then we'll finish off with a quick Q&A session. So just to introduce slightly the overall idea of machine learning, we basically have three types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Oh, sorry. So if I start off with supervised learning, in mathematics, we have a function such as y equals fx. The whole process involves us inputting x through the function fx to get our output y. However, in machine learning, our training set or our data already has the input x and the output y, and our entire task is to find the corresponding fx that will make x into y. So supervised learning deals with the use of labeled data sets, meaning that we have our inputs labeled and we also have our outputs decided. So in this example, for example, if we have a labeled data set of bananas and apples, these will be labeled and then put into the machine learning algorithm. The machine learning algorithm will basically set them and separate them into bananas and apples. So the pros with this is that you're able to set the ideal boundary. You make sure that you specify that you want these fruits to be divided into different categories. So it's not up to the algorithm to decide. And because you have all this power, testing and debugging the algorithm is fairly easy. However, on the other hand, there are some cons. In real life, data is often unlabeled and the labeling process can take a lot of time. It also requires a fair amount of domain knowledge. It is also limited. It will not find unknown information. So because we've already specified what we want the output to be, it can't find sort of hidden information that, for example, unsupervised learning can do. If we also input new data that doesn't belong into any of these classes, the machine learning algorithm will classify it anyway. And as a result, training needs a lot of computation time. Next, we have unsupervised learning. So contrary to supervised learning, unsupervised learning deals with the use of unlabeled data sets. So the idea here is that we don't specify what we want our output y to be. We just basically put in a bunch of images. For example, we'll put in images of apples and bananas, and we'll let the machine learning algorithm decide how the output should be. So the pros on this is that it can pick up on patterns that we might not be able to come up with or we might not be able to see. And a lot of real life data is unlabeled data, so unsupervised learning is sometimes the way to go. However, on the other side, a lot of the time the data can be very biased. So there can be more data for one category than the other. It also requires people to really have domain knowledge to be able to analyze the output. And sometimes, of course, the outputs can be uncertain. So if we take the similar example as before, if we input in images of apples and bananas, for example, even though we wanted it to separate into apples and bananas, for example, the machine learning algorithm may separate it into colors, for example. And then last but not least, we basically have reinforcement learning. So reinforcement learning is fairly different from the other ones. In reinforcement learning, we basically have the agent, which makes a series of discussions, and we have the environment that provides new scenarios for the agent, as well as rewards and punishments for each action that the agent makes. So for example, if an agent makes the correct decision, it will be rewarded, and if it's the wrong decision, it will be penalized. So with the pros of this is that it can be used to solve very complex problems that cannot be solved by other learning algorithms. It can also correct the errors it makes during the training process. But on the other hand, it cannot be used in real-time scenarios. It cannot be used to solve simple problems, and the learning requires a lot of data and a lot of computational resources. So to go further down into the specific types of machine learning, in supervised learning, we often have classification and regression. So classification is the idea of separating outputs into different categories, so discrete values. So for example, with our fruits example, they'll be divided into different categories of fruits. Regression, on the other hand, deals with continuous values. So for example, if we want to guess the selling price of a house, the price is obviously continuous, and so we would use a regression model. Supervised learning is task-driven because we have the input X and we have the output Y, but we don't have the task process in between. Next, we have unsupervised learning. In unsupervised learning, for example, we have clustering. Clustering is the idea of finding similarities between different groups of data in a data set, and then clustering them together and grouping them together. We also have anomaly detection. The task here is to find what's normal in a data set so as to recognize what can be considered as abnormal. It's also called as outlier detection. And unsupervised learning, because we don't have the Y, this is data driven because we don't specify what the output Y should be. And then last but not least, we have reinforcement learning, which is mostly about decision making, as the whole process involves the process of learning from mistakes. I would just like to mention here that this is not an exhaustive list, so these are not all the types of machine learning, but these cover most of the important ones as well. So with regards to the challenge, the AI and 5G challenge, most of the problem statements involve supervised learning. So I'm going to be focusing a little bit more on supervised learning. So as I've just already mentioned, supervised learning can be divided into classification and regression. So hopefully these two graphs are a little more informative. Again, classification divides the data into two or three different categories, whereas regression takes continuous values and finds a relationship between the X inputs and the Y in continuous values. So with classification, we have things such as nearest neighbor, decision trees, random forest, and logistic regression. And with regression, we have things such as linear regression and support vector machine. However, as you probably all know, some of these can also be used for both classification and regression. So for example, support vector machine can be used for both classification and regression. So I'm going to be introducing the data set that we'll be using today. This is the data set from the 2021 radio link failure challenge from Turkcell. So in this challenge, we're dealing with radio links. So in certain regions, we still use radio links to connect multiple sites together. These radio links are susceptible to various weather-related phenomena. So the problem statement was all about using weather-related data to guess whether the radio links would fail or be okay. However, because the data set is incredibly large, today we'll just be using the KPIs from the radio links. So these are the basic metrics that we'll be seeing today. And just to take a look at the data real quick, I'd just like you to focus on the very right where it says RLF. RLF stands for radio link failure. And just to clarify, false is for when the radio link is fine, and true is for when there is an actual failure. So just to go over the building, training, and testing the model process. So this is mostly for supervised learning. So at first we have to split the data and define the inputs and the output variables. So in our problem statement, basically what we'll do is X will be the metrics that we saw here. So for example, we'll put in things such as frequency band or link lengths or error seconds, for example. And then the Y will be basically our radio link failure prediction. What we'll do is we'll split the input and output variables into 2 or 3 subsets. So we'll have some as the training data. The training data will consist of 70% or 80% of the original data set. The test data, which is the unseen data of a smaller proportion, about 20%, which is used to assess the performance of the trained model. And then sometimes you can split your training data and use a proportion for cross-validation, which is primarily used to estimate the skill of the model, and it helps fine-tune the various hyperparameters. Then we're actually going to build the machine learning model. So this process involves defining the model and setting of hyperparameters. So hyperparameters are basically used to fine-tune the accuracy of your machine learning model, and they're often classified as model hyperparameters, which influence the performance of the model, or algorithm hyperparameters. So algorithm hyperparameters do not influence the performance of the model. They only affect the speed and the quality of the learning process. So for example, we have here learning rate and batch size. And then the last step is the training process. So during the training process, the defined model is basically fitted to the training data during multiple training cycles, which are called epochs. After your model is trained, you want to know the performance and accuracy of your model. So for this reason, the evaluation step, which comes next, is a very important stage. Just to mention here before we move on, some algorithms do allow for setting an early stopping hyperparameter, which basically stops the training process if the accuracy of the model doesn't improve after a certain number of cycles. So this is obviously something that should be considered. So for our for our general metrics for evaluating our model, so we first have the general metrics. This is obviously something that I'm sure you already know, which is mean absolute error and root mean squared error. Mean absolute error is basically average of the absolute value of the difference between the original and the predicted values. And then the root mean squared error doesn't take the absolute value, it takes the squared value of the difference and then takes the root of that. And then we have metrics that are specifically for classification problems. So our overall accuracy score is the accuracy of the ratio of number of correct predictions to the total number of input samples. And then we have the confusion matrix. So a confusion matrix is a matrix which describes the performance of the model. So each row of the matrix represents the actual class, and each column represents the predicted class, or vice versa. The matrix basically allows you to quantify the accuracy of your classification. So how much of the information has been correctly classified or incorrectly classified. This matrix or this can come in the form of a table, or it can come in the form of a graphical output. So for example, a heat map. So within this confusion matrix, we have recall, precision, and F1 score. Recall is the number of correct positive results divided by the number of all relevant samples, and the higher the recall, the better. Then we have precision. So precision is the number of correct positive results divided by the number of positive results predicted by the classifier. Again, the higher the precision, the better. And then finally, we have our F1 score. F1 score basically takes the harmonic mean between the recall and the precision. The number is between 0 and 1.0, and we often want to attain a score that is close to or higher than 0.9. So with all these, as we've seen, there are many, many different types of machine learning algorithms. So how do we choose? Well, your choice of a machine learning algorithm really depends on the data set you have, the size of the data set, the outputs that you want, and each situation is fairly unique. But there are some things that you can consider. For example, the size of your training data. If your training data is on the smaller side, or if the number of observations is smaller than the number of features, for example, you want to choose an algorithm that produces higher bias and lower variance. On the other hand, if you have a large number of observations in comparison to the number of features, you want an algorithm that produces higher variance and lower bias. And then we have accuracy and interpretability of the output. So higher accuracy means that the prediction of the model is very close to the true response, the actual value. High interpretability means that the model's predictions are easy to understand from our point of view. So to go into this a little bit further, some algorithms are called restrictive because they produce a limited number of shapes on the mapping function. So for example, linear regression can only produce relations of straight lines. So this is restrictive. But on the other hand, there are some algorithms that are considered flexible because they have many shapes, or they can create many shapes on the mapping function. So for example, if you have k and n, k nearest neighbors, where k is 1, then it's obviously incredibly flexible. So normally, if inference is the goal, then restrictive models are easier to understand. But if you are pursuing higher accuracy, then flexible models are obviously a little better. And then last but not least, you do have speed. Oftentimes, higher accuracy usually means that the model requires a longer training time, and algorithms with higher accuracy also require much more training time. So depending on which one you're trying to pursue, obviously you can decide on your different algorithms. This is just a quick cheat sheet that I've left here. This should give you sort of an overall view of what you might want to choose depending on what kind of data set, what kind of output that you have. These are just references that I've added here. This PowerPoint slide will also be uploaded on the GitHub later on, so you can just look through here if anything's interested you. So we're going into our Jupyter Notebook practice. So as mentioned in the email, the Jupyter Notebook session today will be very hands-on. So we'd like you to follow along, typing the code on your computer as you go. But before I just open that, I would like to explain the algorithm we're using today. We're just going to be using a very simple logistic regression. So just to very briefly explain what it is, today we're going to be using the function y equals wx plus b. X being the inputs and Y being the output, and W being the weight of those inputs. X is obviously the features. What logistic regression does is it takes the Y calculated from W and X and it inputs it into a sigmoid function, which is the Fy that you can see on the screen now. The graph is on the right, that's the sigmoid function. Basically, the sigmoid function compresses the values between 0 and 1. And what we can do is we can set a threshold to decide, okay, so if the number or the result of this is higher than, for example, 0.5, we'll classify this as 1. And if it's lower than 0.5, we'll classify this as 0. So like other algorithms, we do have a cost function to determine whether the answers are far off from the correct response or not. We're going to be using a log loss function, and to choose the different weights, we're going to be using gradient descent. So we're going to go off to the Jupyter Notebook. So again, the Jupyter Notebook should be on the GitHub. I'm going to give 1 or 2 minutes for everyone who's interested to open up the Jupyter Notebook on their computers. You can download the file directly on your computer and open it there, or you can open it through Google Colab. So just a minute or two for everyone to open that. And please stop me if it's too fast. Right, so I will begin. We first need to get the data. So the getting of the data is actually slightly complicated. I'm going to stick the code, or you can directly copy it from the original notebook as well. We're going to be using this code here. This should download the file. Oh, make sure to copy everything. So we'll again leave a minute to have everyone download the files. And this basically gives us, this also includes the weather data, I believe, but we're only going to be using, again, the KPIs. So once you have done that, you should have, on your computer, you should find a file that is called RLF prediction ITU AI ML challenge data. And so what I'd like you to do from here is I'd like you to decompress it manually. This is. And so I will give everyone just a quick minute for this to get done. If anyone is having issues, please ask on the chat.
In the meantime, as you are downloading the dataset and decompressing it, can you please just respond to this quick 5-question survey, please? Yeah, we'll wait for maybe another 30 seconds or so to get the questions. And then we will proceed with everything.
So I will begin again. Hopefully everyone has also decompressed their file. Once you take it out, you should be left with a file that says region a.zip. So if you do not have that, please let me know. Oh, in addition, I have also created a folder called data, and it is there. So if you have it somewhere else, you may need to access it a bit differently from the way I will. So we first will put in our various libraries, namely pandas. And then we're going to basically put our path to the zip file that we're going to access. So for myself, it's in a file called data, and the file we want to access is region a.zip. And then we're going to then type in the code that is going to directly open it. This one I will also leave in the chat. Or you can again directly copy and paste it from the original file. So here, this should open up our file and convert it into a data frame. Oh no, sorry, this one just opens it up. And then we need to input the code to open it up and put it into a data frame. So I will also add that onto the chat. Again, so this part basically reads the file into a data frame. So let's take a quick look at how our data looks. So df.head will give you the first 5. Otherwise, you can just put df and see the whole thing. Again, as I've already mentioned, these are the KPIs of the radio link, and on the very right, you have the radio link failure column here. So this is the part that we basically will want to predict. Again, you can do lots of things to try and maybe find out more about your data, see what it looks like, what the number of counts are. For example, just really quickly, I might count the values of the radio link failures. So the number of falses and false and truths. So as we can see here, this is sort of corresponding to what I mentioned earlier. We have false in the number of millions actually, and true in the number of thousands. So as you can see, we already do see a bias here. So again, after this, you do want to go through your data a little bit more to see how it is, maybe to check if there are any null values and things like that. For right now, we're just going to go straight into cleaning up the data a little bit. So again, as I mentioned, the problem statement is to basically take these various metrics and predict the radio link failure. So right now, this radio link failure is only giving us the radio link failure for these dates. So what we're going to do is we're going to add columns on the right to get, for example, on this row, we'll get radio link failure values from other rows for days in advance. So what we're going to do specifically is we're going to add radio link failure values from after 1 day to 5 days. So I'm just going to show really quickly how we'll do that. We're going to create a new data frame. And again, if you don't know what these metrics are in the presentation, which I will attach later. But basically, these are just taking date time, site ID, and MLID. I think it's just, I've forgotten which one this is, but it should be just one of the few metrics of the ID. And just to see if that's gone okay. It's just taking these 3. And then what we're going to do is we're basically going to create those new columns. So first we're going to create columns of the next 5 days of date time. So this is how many days in advance we're going to predict. So it's going to be 5 days. So this part I'm also going to just copy and paste. Again, you can find this on the original code that should be on the GitHub. So what this is doing right now is for I in the range of prediction interval, which is currently 5, we're going to basically add a new column on the df labels data frame, and we're going to loop through it. And basically we're going to add the date time of the next 5 days. So if we take a look at this, we can see that we now have new columns of the next 5 days. And to just check that, the original row is the 31st of December 2018. And so the next 5 days is the 1st, 2nd, 3rd, 4th, and 5th. So now that we've done that, we basically want to merge this to the original data set so as to get the radio link failure values for each day. So if I just quickly put that down. So this is slightly complicated. But basically what it does is we're going to take a part of the data frame here, which involves basically the features that we picked up and the radio link failure column. And then we're going to loop through our prediction interval, which is again 5, as we decided here. And then we're going to, the target of the column is these columns. So t plus 1, t plus 2, t plus 3, t plus 4, and t plus 5. And then we're going to use the merge to merge the two data sets together, so temp and df labels. And what this does is this is basically going to take the radio link failure of these each dates and create a new column on the side showing the values there. I will just run this to show it. This may take a little bit of time. Okay, so as we can see here, it's done exactly that. It's taking the radio link failure of all the days after this one, and it's basically inputting it as so. Okay, so basically what we're going to do, or what we would like to do in the future, is we would like to either predict the day after, so just after, or just 5 days after. So what we're going to do is we're going to create a new label. And then this as well, I'm going to stick and paste into the chat. So we've made a column of the prediction of after 1 day, and then we've got a new column of the prediction of 5 days. So what this does is it basically takes the idea that if any of the values are true, it will make it true. If that makes any sense. And then basically we're going to finally create our final data frame that we'll be using. So we're going to merge it back to the original data set. So basically what we're doing here is we're just dropping all the rest of these columns here, t plus 1, t plus 2, t plus 3, and we're all just taking out all of these as well, and just taking the 1 day predict and the 5 day predict. And then we're just going to merge it back to the original data set. So if we take a look at this, we should be able to see this. So again, basically we've added these new columns here. And then just for simplicity, what we would basically like to do after this is we would like to basically encode these values, for example, or drop them if they're unnecessary. But to simplify things today, we're just going to take the continuous values here. So we're going to drop the other ones. We're going to drop, for example, TIP or ML5G. We're going to just drop all of these and keep the continuous values over here. And again, this is just for simplicity today, but any other time you may want to keep them depending on how they affect your output. So again, just to make this a little quicker, I'm going to stick and paste from the original code. Again, so this just takes the values here. So they're just going to take the error seconds, for example, and all the continuous values. And this right here. And then we'll take a look here. And as you can see, we've just dropped everything else. And then what we're going to do is we don't want to deal with these false and true values. And so what we're going to do is we're basically going to one-hot encode these so that we can get ones and zeros as answers. So we're going to clean it up by using the pg.getDummies. Oh. No, it's turned up. Let me move on. Ooh. Oh, it won't let me move on. Please give me 2 seconds. It won't let me move on. I do not know why, and I believe we are also slightly running out of time. So what I will do is I will slowly explain the code. So basically what we want to do from here is we want to take just the true and false values and change them into zeros and ones because we want to categorize them as zeros and ones. And then what we're going to do is, as you saw below here, there are a lot of null values here. So we're just going to drop them for the time being. Obviously, in other cases, you might want to do something else with them, but in this case, we're going to be doing that. And then what we're going to do is we're going to take just a fraction of this. So again, this may not always be a good idea, but because if you use the entire data set, it will take a long time to train your model. We're just going to take basically 10%. And then we have to reset the index so as to make sure that it goes back from 0 and categorically, because this will just take a random sample of 10% of the data. So this basically creates a new data frame called sample df. And then here is basically where our training starts. So as you can probably see, the data preprocessing part takes quite a long time. I wanted to go through this one by one, but unfortunately, because we're running out of time today, I'll just run through this very quickly. So as I said, the X is the input value. So we have to put in the various metrics that are then going to be used to predict our final output values. So in this case, what I'm going to do is I'm just going to drop these columns, 1 day predict true and 5 day. And sometimes you may want to instead predict the 1 day predict, or you may want to do the 5 day predict. That just depends on what you'd like to do. Today, I'm just picking up on the 5 day predict. So the output here I've set as 5 day predict true. And then from sklearn model selection, we're going to take in train test split. And we're also going to bring in standard scalar. And then we're going to split these into training sets and test data sets. And then also here, I have scaled this. I did mention this last time in the data preprocessing session. This might not always be a good idea depending on your data set, but today I've just decided to scale it as it worked better that way. So here is the general part, the logistics regression section. So from linear model, you're going to import logistic regression, going to create your logistic regression model like so, and then you're going to fit in your scaled X training data and Y training data. This is the accuracy score as mentioned. And then from sklearn.metrics, we're going to import a classification report. So this classification report is the classification matrix that I was talking about. Basically, it will give you a report of all the metrics that was mentioned, for example, the precision, recall, and F1 score. And then basically, we're going to call the model and then .predict and input our test and call this predictions. So basically what it's going to do is going to predict it's going to predict values using the testing data. And then we're going to print out our classification report to basically see how well it did. So as you can see, this is terribly bad. One reason for this is obviously because there are much more zeros here, which is the false, and there are much, much less trues here, which is 1. So there's only 34 in comparison to 65,730. So obviously, as I mentioned before, this is incredibly biased and probably not the best way to go about doing it, but this is just an overall run through of how you can. So this basically just uses the logistic regression from the sklearn library, but you can also define logistic regression, so you can build your own model from scratch. So what we can do with this is we can just define a class of logistic regression. So what you'll need here is you will need a sigmoid function here. This basically just follows the equation that I gave earlier. You need to also show your cost function, which takes in the log loss function. You need to have a function that fits the data as well. And again, this, if you go to the original code, it should give you some comments on what each step is doing. So if you could just take a look at that while going through. And then you do also need one place to predict your answers. So here I've chosen the threshold as 0.5, but you may want to set it to 0.6 or 0.7 or smaller than that, depending on how your data set goes. And then ideally, you would just call it like we did earlier with here. You would fit your training data, predict it, and then get your classification report to see how well it did. So arguably, it did very, very slightly better than the original. So ideally, this is it for the model building section, but there are obviously different algorithms that you can use. And on the original Jupyter notebook as well, we do have an example at the very end that uses XGBoost. So again, because of the type of data set that we were using, because we very much simplified it, we do not get very good results. But XGBoost is a lot quicker than the original logistic regression. So even if you don't take a fraction of your data, you might be able to just run it and see that the final classification report does improve. So just to go over it really briefly, it's basically just the same. We would call in our model XGB classifier. You do have to set your N estimators, and then you would fit the model. You would bring in your accuracy score, and this is just to basically plot how the loss went throughout the training process. So as you can see, the model is overfitting because the training and the testing is exactly the same. So again, it's not gone incredibly well, but hopefully this gives you a brief overview of how model building and training a machine learning model goes. Okay, that's it for myself.
Okay, thank you so much. Probably we are running out of time, but maybe we can take one or two questions if there is some questions or comments from everyone on the participating in today's session. Please, if you have some, even comments are welcome. So anyone, you can just open your microphone and let us know if you have some comments.
Sorry, I did see the comment earlier about using a laser pointer. I apologize for not seeing that earlier. For the next mentoring session, I will do that.
Okay, looks like we have no comments. I hope that these sessions are helpful to some people who are participating in the challenge, or maybe to others it might be a refresher. But yeah, inform us if you have like some topics that you are interested in that you'd like to see us to cover or to talk about. That would be interesting. Maybe Vishnu, if you have some comments, I give you the floor.
Thank you so much, Thomas. Thank you, Miya. The excellent session. Maybe the participants who followed along can maybe give some comments. For example, I was trying to follow Miya with this collab. There is a button, right? You can click on open in collab and you can follow along. And that's what I tried, and I found that I had to change the path to include the / content instead of data. That's a small change. Maybe it took a couple of minutes for me to figure out. But other than that, I think it was pretty smooth. If somebody else had some other comments, for example, if you face some problem following me, or if you have some questions, please. Otherwise, I think this is really good and some session. Thanks a lot.
Thanks, Vishnu. So anyone who was following along, do you anyone with comments? And of course, if you have some suggestions on next topic that we should cover, you can also, maybe we can open up this platform to just get some ideas. Yes, about the recording, we are going to release the first session next week on Wednesday, and then the other sessions will follow up. So please bear with us, but we'll provide them on YouTube as well as in the neural network on the Air for Good platform. Okay, so it seems like there's no comments. So thank you everyone for joining the session today. We did appreciate you taking the time and taking part of these sessions. We hope that they are helpful or they will help you in some way. And please participate in the challenge in some of the problem statements. We are looking forward to having your solutions and you being part of the challenge. So thank you so much and have a good day.